and sorry for the hiccups. But yeah, let's move on with some multi and univariate statistics. I will talk a bit about the multivariate statistics, and afterwards, Philip will talk a bit about the univariate part. And then we will have a break, and after the break, we will let you work on the notebooks on your own. I just need to figure out how to move on with the slides. Yeah, now it works. Yeah. Okay, just to very briefly, what I'd like you to take home from this statistics session, basically, as Absar already mentioned, there is really no one size fits all. So it's extremely data dependent, and in most cases also there will be many different options that are a good way to analyze your data. So there might not be one single test that's appropriate for your data, but there might be many different ways of how you can explore your data. And for this stat session, we just have collected some examples on how you could look at your data, but those examples by no means are exhaustive or the only way you can look at your data. And so I think one really crucial thing is that you always check the assumptions of the tests you're using. So for example, does your test assume normal distribution? In that case, before you use the test, check if your data is normally distributed. And if not, then of course you need to do some transformation to make it normally distributed. Also, another question could be, is the test okay with having zeros or NA values in the data? And in that case, you might have to consider imputation, or you may go forward with the zeros in the data. And so methods also continuously evolve, and there's always better things. And as we study, we get more knowledge. So I think one really crucial thing is always that you document your methods in great detail. If it doesn't fit in the material and method section, then put it in the supplementary information. I think that's really the most crucial thing, that researchers later on can understand what you did and reproduce the results. And also, I think it's really important that you make your scripts publicly available. This is, I think, again, to enhance fair data principles and to make your research reproducible, but also to create trust in your research, as I think Martin and Philip showed nicely in the QC session. That brings us basically back to the QC. So you need to show what you did with your data. And I think that is also a really nice thing you can do, even though you cannot share your raw data, for example, but you can always share your scripts. Yes. And so we will talk a bit about the multivariate and univariate statistics. Basically, the difference here is, as the name already tells, the multivariate statistics look at multiple features, or in our case, metabolites at one time. So it's more methods that you can use to explore patterns or trends in your data. And then the univariate methods, they look just at one metabolite at a time. And for the data we are working here at the summer school, we have selected a few examples of multivariate and univariate statistics. And for the multivariate parts, we will show you a bit how to do a principal components or coordinates analysis, as well as a permutational multivariate analysis of variance or permanova. So that's what I'll be talking in the next few slides. So within the multivariate statistics, we have methods that assume a given structure. So that's the supervised methods. With those methods, you may do, for example, predictions. So a question could be, if I know the status like diseased or non-diseased, is there a metabolite that can predict this status in my data? Examples are PLSDA, random forest, or XGBoost. There's many, many more. Those methods we will not talk about in the next session, as they would be out of scope and we don't have time enough, but we will talk a bit about the unsupervised methods, in particular PCA, PQA, and Permanova. And those methods are unsupervised, so they don't assume a given structure in your data, but they are seeking for a structure in the data without prior knowledge. So how does principal component analysis work? In very simple terms, if you imagine you have a couple of samples, let's say different sample types, plasma, urine, and skin samples, then what PCA would do is it looks at correlation. So it looks at how does my sample 1 correlate with sample 2, and then how does my sample 1 correlate with sample 3, and so on. And so you can, of course, do this if you have very few samples and few features, but it really gets not overwhelming if you have thousands of metabolites and thousands of samples, as we do in a metabolomics experiment. And so basically PCA deals with that by transforming those correlations into a two-dimensional plot, where the highly correlated samples would form clusters in this two-dimensional plot. And also the axes are ranked in order of importance. So that means, for example, the urine and skin samples would be more different from each other on this plot than the urine and the plasma samples, although their distances are equal, but the principal component 1 is of higher importance. So that means a higher difference in the samples. Then we also have the principal coordinates analysis. So that's something a bit different, but very similar. It's also called classical or metric multidimensional scaling. And basically, instead of looking at correlation, PQA converges the distances among the samples into a 2D graph. And so, interestingly, a principal coordinates analysis using the Euclidean distance is exactly the same as a principal components analysis. So it matters which distance metric you use. So just to illustrate this also, how the principal coordinates analysis would work, basically, it would look at dissimilarity between plasma and urine samples, and then plasma and skin samples, and so on. And out of this, it would create what we call a distance matrix, where you have a diagonal filled with zeros. So there's basically no difference between the plasma samples because they are identical, right? But then you would put in the distances across each of the samples in that distance matrix. And so the output would look actually exactly the same or very similar to a PCA. Now, there are many different ways of how we can calculate those dissimilarities across samples. And I think Florian illustrated really nicely in the Match MS session yesterday, such as for chemical similarity, it's almost a philosophical question of how do we define dissimilarities across samples. There is many different metrics you can choose from, and each of those metrics will basically show you a different reality of your data. I think what is important here is that also, like mentioned before, you check the assumptions of the given distance metric. For example, some distance metric, like the Frey-Curtis metric, was developed in community ecology, and it assumes count data. So one question you could ask yourself is, do relative intensities in mass spectrometry, can they be seen as count data? And also if you, for example, scaled your data previously, you will have negative values, and a Bray-Curtis distance, for example, would not work and in such a distance matrix. So you couldn't scale your data if you wanted to use Bray-Curtis. Other distances, for example, the Euclidean distance, it doesn't deal so well with zero values. So here, it's of course important that if you want to do a PCA, that you have your data imputed and don't have any zeros in your data. Also, some other metrics like the Jacquard distance, for example, it assumes binary data, so zeros and ones. So if you are more interested in the qualitative differences, like which metabolites are present or not present in your sample, you could, for example, choose the Jacquard distance. So here, this is just basically to summarize again when you're at home, what I just told you here. There is also distances that are chemically informed, so they have been developed in more recent years. So with those metrics, basically you take into account the chemical structural similarity of the compounds you measure. So that could be something interesting, maybe that you want to read up later on. The presentation is, yeah, now it's going. And so the next question is then, of course, so a PCA or a PQA basically only shows us a visual representation, right, of our data, but it doesn't provide a statistical value of if those differences are significant or not. And to assess statistical significance of those clusters, we can, for example, use a what we call a permanova, a permutational multivariate analysis of variance. And so what a permanova does is basically it tests whether two or more groups of samples are significantly different based on a categorical factor. That means your metadata, like what sample type it is, or if it's a diseased person or a healthy person, and so on. It is similar to an ANOVA that you might be familiar with, maybe, but it operates on the distance matrix, so that matrix that we also use to create a principal coordinates analysis. And so the typical value that it would retrieve is a pseudo F value, as well as a p-value. So here, of course, like if you put the significance value in 0.05, if you have a p-value of 0.025, that would mean you have significant differences across your different categories or your different clusters. And then the Adonis R-squared would show you how much of the variation in your data is explained by this specific metadata category. So in this hypothetical example here, it would mean that 35% of the variation in your data can be explained by your different sample types, like bacteria, corals, environment, food, and so on. And I think with that, we can move on to the cluster analysis. We will also do some heat maps and cluster analysis. Here, just very briefly, a heat map is basically, you can imagine it as a graphical representation of your feature table, where values that are high can, for example, be colored in red, and values that are low are colored in blue. And of course, you want, the aim of the heat map is also that you see patterns. So you want to avoid something like you see on the left side, where you cannot see. It's basically random color distribution. And for that purpose, you can cluster your heat map. That means you can group together rows or columns that are similar. And with that, it will be more easy to highlight trends in your data. And we will show you as well an example in the notebooks where you will work with your own data. And I think with that, we can already move on to the univariate part.
All right, so let's see. Yeah, so as Madeline said, in multivariate statistics, it's the situation is that you have more variables than observation. Whereas in univariate statistics, it's the other way around. This is the typical case, right? So you have many observations, but not that many variables, right? However, it's not always the case, especially in metabolomics. That's typically not the case. It doesn't mean that univariate statistics is not valid to use, but it means that there are certain things we need to think about. So when we analyze several different variables using univariate statistics, it will lead to many separate tests, right? And there are implications of this. Typically, you will do some kind of hypothesis testing, right? So you are interested in a p-value eventually. So what the p-value says is then the probability of obtaining the observed results, assuming no true differences. And commonly here you have a threshold of 0.05, which translates to 5%. So basically, it means that there's 5% chance that this is a false finding. So this seems to be okay, right? 5% is fine, but in metabolomics data, then you might have very many variables. In our data set, we have 5,000 features. So how does that affect the interpretations of these p-values? So, of course, if you do 5,000 independent tests and there is a 5% chance of them being false positives, it will mean that you will have 250 false positives. And that's kind of a problem, right? So it's something that you have to think about when you use univariate statistics for metabolomics data. But luckily, it's something that we can take care of. So there are several ways to correct for this that you usually call multiple test correction. So the most conservative method is the Bonferroni method, where you just divide the p-value threshold, in this case 0.05, with the number of independent tests that you are performing. And then you get a new threshold. So if your result is considered to be significant, it needs to be below that threshold. So in this case, 5,000 tests, we end up at 1 to the power minus 5, which is quite low. Of course, this assumes that you run 5,000 independent tests, which is not really true in metabolomics. So this is quite harsh because, of course, metabolites correlate with each other. So they're not truly independent. So a lot of people think that this is a bit too harsh and too conservative. And luckily enough, there are methods that are less conservative, that are still valid. And the most common, I would say, is to use the Benjamini-Hochberg method, or also called sometimes FDR, for false discovery rates. So basically what you do here is that you find, so if you have two groups that are the same, that you want to compare, and you have two identical, maybe two individuals just sampled over, two individuals with the same group sampled over many times, and then you do a lot of tests, many variables, then you will expect like the p-values to be kind of spread out here randomly, the blue bar, basically. So they're random, they're somewhere between low and 1. So basically what FDR method is doing is to find this background, this expected distribution that you expected if there were no differences. And then instead, numerically, it finds this little piece up here, which is the true positives. And if you want to understand this more in detail, I would recommend you to follow this link to this excellent video by StatQuest, which I think is awesome. So if you go on to the analysis tasks that we have ahead of us now, the data set that I have been working on the whole week, we have a situation something like this, right? So we have, this is the metabolites. We have the peak area on the y-axis and then several time points. We have two different sample types. So this says something about which statistical methods we can use. So typically you would use something normal like a t-test. Here doesn't work because t-test assumes that you have two different groups that you want to compare. Here we have actually 6 different groups, 6 different time points. A normal way then would be to use, for example, ANOVA that can take care of that. Compare the means of several different groups, but we'll go into this in detail. The aims, I guess, will be to investigate if there are metabolites that are statistically significant across these different time points. First in plasma, and then we look at these metabolites in detail to see if they're actually detectable in skin, to see if they can be used as a biomarker already in skin, which would be good. So, but how do we choose the method? So I said ANOVA could be an alternative, right? We have, it's good because it compare the means between several different groups. However, there are several assumptions. So you have to think about normality. Assume ANOVA assumes that you have normal data. And then it's whether the samples are independent. And that's something we will discuss these two concepts a bit more. So statistical independence, let's assume we have this situation, right? We have 4 different groups. They might be, for example, people eating different diets. So it might be vegetarians, vegans, people who eat vegetarian plus fish, and people who eat everything, right? Then we sample them, we measure metabolite, and then we want to know, is this metabolite different between these? Then we could do an ANOVA, something like that. We have 4 different distributions. We see, are these means actually different? In this case, it's a bit different, right? Because we are not really comparing 4 different groups. We are comparing 4 different time points because these individuals are actually the same. So, I mean, this green dude here at time point 1 is most likely more similar to the green dude at time point 0 than the blue dude at time point 0. So there is a relationship here, right, between this. So it means that we cannot say that our data, that our group are, that we have statistical independence here. So it means that we can cross out these. You cannot do ANOVA, you cannot do cross-code. Okay, we have 2 more alternatives left. Let's look at normality. So normality means that your data will follow this very nice bell curve. That means that you can calculate a mean, you can calculate a standard deviation. However, when you have a skewed data like this, this doesn't really apply. And if we look at our data as it is now, I just took one example here, so this is not representative for all of it. It doesn't look super normal to me, at least not the plasma. It doesn't seem to follow a perfect bell curve. So what a lot of people do is that they transform it. So if your data is not normal, maybe you can force it to be normal. And quite common, you use log transformation, and you just say that, yeah, I use log transformation, and magically all my variables became normally distributed. It's great, right? Unless maybe it's not always working. So in this case, I mean, you look at the plasma values here, it doesn't really look super normal to me. So, I mean, if you're in doubt, if you think maybe your transformation is not perfect, it's better to assume that your data is not normal. And what you can do then, instead of using these parametric tests that assume normality, you can use a non-parametric test. And then we go back to our matrix here. We can cross out also repeated measurements ANOVA, which, because our data, we don't consider it to be normal. So we have one left, that's the Friedman test. And that's exactly that. It's a non-parametric test where you can compare several different groups. So I thought it could be fun to do this by hand, right? So let's assume this data is completely made up. I just added some random numbers. So what you do in a non-parametric test usually is that you perform ranks. So basically, line by line, you just rank them. So lowest one is 100, and then next one is 110, 120, 200. Just to rank them 1, 2, 3, 4. Then you just do this for all the lines like this. This is really boring if you want to do it by hand. So luckily you don't have to do it later. And then what you do is you just take every time point and just sum it. Just sum the ranks. Yeah. And it seems like it's a bit different. We'll see. And then it's also, there is a formula you can use to calculate what you expected these averages to be. This the summed rank. So you can just throw into this in this equation. You can throw in the number of participants, which is 5 in this case, and the number of time points, which is 4. And we do that, and then we get 12.5. So that's what we expect. And they are not 12.5. They are a bit different. So the question is then, can we put this into a statistical context? Yes. So we can use this formula to calculate, this is what the Friedman test does. It calculates this, variable called Q. And then again, we throw in the number of participants here, N, the number of time points K, and then you have this R here, R squared, which is just the sum of all the ranked sums. So it's going to look like this, right? So you take 8 squared plus 11 squared plus 15 squared plus 16 squared, and then you get the value. And then for the Friedman test, you can assume that this value will follow a chi-square distribution. So, which looks like this. So there's a different chi-square distribution depending on your degree of freedom. The degree of freedom is basically the number of time points minus 1. So this curve will look differently depending on how many time points you have. And the highlighted part here are the values that would be considered to be statistically significant given a p-value of 0.05. And then we can plug in the value that we got, which is 4.92, which is here. And you can also calculate the p-value for that, which is 0.80, which means that in the example we had, we could not show that this is that we actually is a significant difference between these groups. So this is something we'll do in the task later, but not by hand, of course. You will have to do this using our methods, and it's going to be much easier and hopefully a bit more fun. Just some final thoughts before we start. There are some caveats, I think, at least when using rank tests for small data sets. And that is, for example, if you look at this, you have 2 different groups. And they seem to be different, right? Actually, all the values in the blue group is higher than all the values in the red group. So, I mean, it looks like they are different. And we can perform a t-test and we get significant p-value. We can perform a non-parametric version of the t-test, a rank test, which is called Wilcoxon, and then we get a significant p-value. That looks good, right? Then we can just look at another comparison. And here you see the difference is much bigger between the groups. So again, if we do this, we get t-test, we get a ridiculously low p-value. It's actually low enough that R doesn't really care to compute it even lower. It's because it's a minimum p-value R will compute. So it's a big difference. What about the Wilcoxon p-value? Well, it's the same. Because already at this case, we had a perfect separation between the groups. We find the ranks, in this case, I don't know how many we are, it's like 8 in each group. Rank 1 to 8 are already in A group, and the rest are already in the B group. So it doesn't really matter if you can see here that clearly these differences are bigger, but it doesn't translate into a lower p-value in the Wilcoxon test. So that's something you need to think about a bit, because in the context of metabolomics here, it can be a bit hard to do multiple test corrections for some of this group. If you only have like 5 individuals, then you don't get very low p-values. So it's just good to think about that. All right. Yeah, this is basically what we do one for any correction for this p-value. Even if it's a perfect separation, it's not considered significant. So it's just good to think about. I think Madeline want to add some final words before we go on to the analysis task. Yes.
Yes. Yeah, so basically this is a completely unrelated and random advertisement in the middle of the course. But I thought if you enjoyed the biobank tours on Monday, we are also organizing a PhD course on biobanking later this year. It will be mainly for students from the Copenhagen University, but also students from other universities can apply. So I just wanted to quickly advertise that. Let us know if you have any questions, or also follow the link that's put here on the slide. We will put the slides online in a second. And should we put Jupyter notebooks on this work? Yeah. So I think what we recommend you doing now before we go to the break is that you open the Jupyter notebooks, both for the multi and the univariate statistics part, and you start loading all libraries. So once we get back from the break, you will be ready to work on your data.